Okay, welcome to thermodynamics. Yesterday, we sort of left it with this slide. And the question is, if you had 800 kilopascals of air pressure pushing on a fluid, and you had a piston that was 25 centimeters in diameter, basically 10-inch diameter piston, basically 120 psi. How much force can you get out of it? So, the way we set that up, force is pressure times area, which comes out of the formula. The pressure is definition, force divided by area. What's our area? It's a round piston, so it's pi r squared or pi over 4 times d squared, because there's 2 radiuses in d. And we know what the diameter is, 25 centimeters. We're going to use that in meters though. And then the pressure is 800 kilopascals. So here's my free body diagram. And I actually didn't write the forces in there. I'm just more of a graphic thing. There's no given. Here's my find. There's my formula. That's what I put in the formula. And if I put stuff into the formula, I got a problem. The problem is these units don't cancel. I know that they probably will, but they don't. And what I have to define is, what is a Pascal? And probably I want to say what is a kilopascal. So I'll say 1 kilopascal. What is that? That's 1,000. Don't forget the K means 1,000. And that's newtons per square meter. Now we're talking. That's going to cancel. And that cancels. And the meters times meter are going to cancel these meters squared. And I end up with units of newtons. And it's going to be probably kilo. I could have left the kilo and it'd be in kilonewtons, but we'll leave it in plain old newtons. So that leaves me the question of we need happy fingers to calculate. I'm going to kind of estimate it while somebody's punching numbers. I'm going to leave this in a kilo. 0.25 times 0.2 by 0.0625. So we got 100 there, so 0.06, and it's going to go 2, 6.
39,269.9.
39. Mathematically precise. And if I was estimating it, I'd say, let's see how we did. 0.6 approximately, or 0.06. 25 and 25 is 625, and a quarter is about 6. And this is 8 divided by 4 is 2. So we've got 200 times 0.06, but the 100 is going to make it that's like a 12 times 3, it's like a 36. And then we got it down. So there 36,000, but this is bigger than 3, so 36,000 plus some, and that's what we got. It's the 39. We're in the ballpark. This is really precise. How much do we really know? we really only know 2 digits worth of precision here, unless they told us it's 0.25000. You know, measured it with laser guided something. And the 800 kilopascal, how precise is that one? It might only be good for 1 digit. Maybe 2, probably not 800.000. So anyway, and most structural saying we got 2, maybe 3 digits. I'll use 3, knowing that maybe 2 is all we got. But rounding it to 3 digits, you got, I'm going to put the kilo back in. I'm going to call it 39.3 kilonewtons. So that's all well and good, but what does that mean? You know, for those of us who are familiar with pounds of force, so that's the answer. Let's put it in a little bit of context. 39.3 kilonewtons. And according to the front of your book, 1 pound force, and that's exactly one, with as many zeros as you want. It's a definition. Where did it go? Is 4.448 and more digits I won't use, newtons. That leaves us, we're going to keep with the kilo. We didn't make the kilo go away. Thousands of pounds of force. So we'll divide that by 4. It's going to be something like 8 or 9 or. We got almost 40 divided by over 4, so it's going to be like 8,000.
I got 824 kilopounds of force.
Okay, thank you. So 8,800-ish pounds of force you're going to get on that 10-inch piston that's being supplied with 120 psi of pressure. So that was so much fun. We'll come back to that page. We have another example, and this one's not about cars. When they measure something that's like 110/80, they're measuring millimeters of mercury, which rho GH, they're telling you the H, and they're telling you what the density approximately is, and that's what they use, 110/80. It's millimeters of mercury. So I want to know just exactly how much, this is the pumping pressure, this is the relaxing pressure that your system's going through every pump. I want to know just exactly how much pressure is that in pascals or psi or what have you. So how are we going to get there? We're going to do a trick with the conversion, and that trick is we don't have to go all the way back to rho GH to solve this problem. What we know is that 14.696 psi is 1 standard atmosphere, and so is 101.35 kilopascals, and so is 760 millimeters of mercury. And that happens to be the unit that we have here. So I'm going to use this to make, these are all equivalent to 1 standard atmosphere. So I'm going to use these relationships to make my my conversion factor and find out I'll just write find. I won't do all the given stuff. So pressure equals, this is all about conversion. We're not actually calculating anything. We're just converting. So if I look at it, if you take is it maybe 7 times this is really close to this? Because you're going to kind of end up with 1/7 times 14. I bet you it's going to be close to 2 psi. That's what.
I got 2.13 psi.
2.13. Is that gauge pressure or absolute? Or a context question.
Wouldn't this be a gauge pressure?
It's gauge pressure because you're measuring the, in this case, the mercury is open like to the atmosphere when they did this. It wasn't like a, but frankly, it's a sort of a pressure. It's really a pressure difference, but it's a gauge pressure. Let's see what that means. In kilopascals. One-seventh of 100 probably is going to be my estimate.
I got 14.6 kilopascals.
And when I'm writing my, when we get to tests, I'll be looking for this too. When you get an answer, you know, is this your final answer? Sometimes people like, I'm not sure, I'm going to do it this way, I'm going to do it that way, and have the instructor pick which answer's more correct. Nah. You know, if you're going to be wrong with certainty. Put a box around it, draw an arrow to it, say, this is my answer. And it also helps when you're scanning a page, like for homework or even for your own use later on. Somebody asks you a question, you scan the page and you look for the line on the side that drives you to a box, and that's an answer. You can find it faster. So that's conversions. Which brings us to the next thing. Manometer equation, and this is not so much about you're going to need to use this for manometer as much as it's a method. We do use manometer. This manometer, basically, if there's more pressure on one side than the other on the loop with fluid in it, the fluid's going to reflect that, and you can measure the difference in height between the two fluids and use it to figure out what the pressure difference is. These days they have electronic means of doing it, but this is, I got this from a guy that retired from doing refrigeration and HVAC stuff. And if you're trying to balance the flow between, like in this room, we don't really have it so much. Maybe, if you want to make sure that the air coming out of the vent in the back of the room was coming out as fast as the one in the front of the room, you'd have a little, you'll see there's dampers. These are all adjustable, and right near the front there's a flap that you can adjust. So how much should you adjust it for? Well, if you took this and you took a tube off the top of it, and you took the tube into the duct there, and you went to the same part of the duct in the back of the room and got the tube and connected them here, and you start it up, and you get, there's usually, it's a red, it'll be fluid with like, so they'll use oil, with red coloring in it, and if it does like that, you go, whoa, this guy has more pressure because it's pushing the fluid up. So you might go to the back of the room or in front of the room, whichever one was, and open one of the valves or close the other one, depending on what you want, until it balances. So the manometer, they actually have used these a bunch. These days they do the same thing, but we have an electronic version of this with it's a differential pressure meter. It's got pressure on both sides, and you can either leave one end open, it's gauge pressure it's measuring, or you can put something, hook it to both sides, and it'll tell you the difference between pressures. But this is a manometer. How hard is it to make? And it's really just, you get a tube and you make a loop and pressurize different on either side.
I was going to ask, wasn't this the same principle behind the ancient Egyptians' water levels?
Yeah, kind of, sort of. Water levels a little bit different from manometer. Manometer's checking differences in pressure. The water level's trying to find a level, and it's going to be level. And it's not just the ancient Egyptians. If you go to the hardware store, they sell a something put on the end of a garden hose. This clear length of tubing that's maybe 3 or 4 feet. And my brother-in-law used this when we were building something to figure out where the level point was to set a beam or whatever. 4 inches of clear tube on either side of a garden hose. You fill the garden hose with water. It had caps on the end so the water wouldn't all come out. And then you put the garden hose up and on both ends, maybe it's 20 or 30 feet away, and you pull the caps off, and it evens out, and then you know where this end is the same height as that one, and then kind of bring up the level water on the one end so it's where you want it to be, and then put the hose on the other end, and then you know that that beam needs to be at that point. And that's every bit as accurate as a laser. Actually, probably more accurate than a laser's nice because it gets you a nice straight line as long as you have precision on the angle. And frankly, if you get far enough away, the laser, any issue you have with the angle of the laser is going to give you an error in where that dot is. But with this with the garden hose thing, 50 feet away, it's going to be just as accurate as it is at 2 feet as it is at 150 feet, in theory. So not just the Egyptians. And this is about measuring pressure. That's a different thing. I have a bunch of these in the back room. These are, they're using a manometer to measure wind speed. If you point something into the wind, and when we get into fluid, we'll talk more about that, but that generates a static pressure that if you know what that static pressure is due to the speed of the wind, you can use a manometer to tell you how fast the wind is going. So it tips into a small angle like that so that you can get finer gradation on the speed. But they use these for, here's an example. You got a reservoir on one side, here's the static pressure and then dynamic pressure. Dynamic pressure coming in pushes this side more, and depending on how far down it pushes it, you can figure out how fast the air is flowing. And that's how airplanes, they don't do it with fluid. Again, they have an electronic thing that's measuring these two things, but that's how they know the airspeed in an airplane. Okay. How do you figure out how much pressure there is? Imagine you have a tank that has an enclosed space, and you want to know what the pressure is inside the enclosed space. And what you know is the level of water in the tank, the tube coming out with the manometer, and maybe there's you know, it's natural gas in the tube, and then you got water, but you didn't. Maybe you got some oil and you got water and you got mercury. I don't know why you do that, but if you did, we can solve that problem. And the way that goes is, if you go from a known pressure, subtract rho GH, but there's a trick on the H to do that. For each fluid, you measure the H, you have the density, gravity is going to stay the same. Subtract rho GH. So basically, the pressure that you're looking for is going to be the known pressure minus the sum of these things, but the trick is H. If you have, on the fluid that has whichever rho you're dealing with, if you start from the one surface of that fluid and go to the next surface, wherever it is, if you measure down from the first surface, you start at P1 and come to the first fluid surface, the liquid surface, if you have to measure down, that's negative, which turns that term into a positive term. And if you have to measure up, that's positive, which makes that a positive here, makes it a negative term. And if you think about it, that's what you want. If something is higher, then the pressure here that's pushing it up is a higher pressure than your standard pressure. So that double negative reinforces the pressure thing. So this is, I emphasize this not because manometers are especially useful, although they are useful, but having 17 different fluids and a whole bunch of loops like that, not that many places where you run across that. But getting comfortable with a formula that when you understand the formula, you don't really have to think about which end is up and whether you're adding or subtracting, you just go with the formula. As long as positive H direction is up, fluid's got to be stationary and it's only influenced by standard gravity. It's not like bouncing around. This is a method that you can use to answer a question like this. I want to know what is the pressure in the air here. What I know, I want to gauge pressure. Because I'm going to measure it relative to, this is open to the atmosphere, so I'm measuring it relative to the atmosphere. So P1, here it goes to P2, I want to know P2. My P1, if I'm measuring gauge pressure, that's like 0. It's atmospheric pressure. If I want an absolute, my P1 would be whatever the atmospheric pressure is, 101 kilopascals. But if I'm doing in terms of gauge pressure, I can say atmospheric pressure is here, that's what I'm measuring things relative to. So what would a gauge read if I put a gauge on here? I didn't have a gauge on here. Maybe I need one, but I want to know what that pressure is. So for the first term, this fluid, which happens to be mercury, and we wanted to isolate the mercury from the water because we don't want to drink mercury. And we're isolating it, it's open to the atmosphere here, but we're isolating it with some oil that doesn't absorb water and doesn't absorb mercury. That's essentially context to why you do that. Although these days you don't use mercury for anything because it's a neurotoxin. But so for the mercury, you have to come down from this is the pressure I know, and now my H is measured negative direction. So the H would be negative. And now for the oil, from this surface it goes around and come to this, but I have to measure up. And what's really going on here, this loop, the fluid in this, if you think about just the loop there, the fluid in this side of the loop is pulling down this way, and this one's pulling down that way, and they balance each other. You could just pop that straight across and have the same thing, but maybe you needed that loop for whatever reason. And same thing with the mercury. The mercury here is pushing down, and this one's pushing down, and they're equaling themselves. All that matters is the difference. And then for the water, so we don't care about this. This loop can go way down. This could go up half a mile. I don't care. What I want to know is the difference from this circuit, and that's going to be a positive H, because it's measuring from this fluid surface up. That's the difference. And then for the water starts here and it goes all the way to this surface. That's going to be measuring up. And when I get to that point, and they did the numbers differently, I'm calling that 1 and 2. I don't know. They're saying that's 1 and this is 2. We're going to figure out what the air pressure would be. So I'm going to say, I'll just say P air. Pierre. Pierre. I know people named Pierre. And then P atmosphere minus sum of rho GH. Equals, I'm going to say my atmospheric pressure, I'm going to say P air gauge. So my P atmosphere is a 0 because that's my reference, minus rho 1 GH1 minus rho 2 GH2 minus oh boy, I don't like my numbering. I'm going to change my numbering here because I want to start from here. So the first thing was,
Isn't that equal to 1?
what's that now?
Isn't the P air at 1 ATM?
Yeah, it's 1 atmosphere. I could write that in here, but then that wouldn't be gauge pressure. Since we're doing gauge pressure, it's relative to atmospheric, and the absolute pressure would be 1 atmosphere plus or minus whatever. So works either way. I'm gonna leave this as a 0 because it's a reference. I'll say it's ref. And the first thing was mercury, and that's 13,600 kilograms per meter cubed is the density. 9.81 meters per second squared is gravity, and the height, it's measured let's bring us a little tighter. I'm measuring, it's down, so it's a negative, and the data tells me it was a negative 0.9 meters.
You want just because you did use 900 on the top, you flipped up on the drawing, you did H3 was H1.
Yeah, see, the problem is the numbering in the example went in this direction, and I want to go from a known to my unknown. So this is this H1 in the example.
But H1 the example is 0.5. You used 0.9.
Yeah, but that was H1 in my example in the book.
Correct.
So I'm starting here.
You're just going to flip the values.
I flipped the numbers to go 1, 2, 3, and I got to change the example, I guess. Whatever happened, this is a 0.9. And now I'm going to take the next term and I'm going to subtract
Can you scoot the paper up, please?
Oh, yeah.
Thank you.
For the next one, I'm going to subtract again rho GH, and now for the 2 one's going to be the same, I bet. The oil height, and oil has a density of 855 kilograms per meter cubed, 9.81 meters per second squared, and height on the oil, it's going from here, it's measuring up. So I should put arrows in the directions that we're measuring from. This one measured down, so it's a negative value. This one's measuring up. And this one's going to be measuring up. So that height 2 is 0.750 meters. And I'm leaving these separate because I'm going to calculate them all separately and then add them together. And then for my third one, the density was water. That's 1,000 kilograms per meter cubed, 9.81 meters per second squared. And the height on that one, we're measuring up, so that's a positive H, which is 0.90 meters. And now we have conversions. Kilogram meter per second squared is a Newton. And we have a meter here that's going to cancel one of these and leave me with a squared. So I get newtons per meter squared, and I can say 1 Pascal is 1 Newton per meter squared. And we're left with units of pascals, which is what we were hoping for. So this first term,
Professor,
yes,
last
sir.
line, it's 0.7, it's instead of times 0.9, it's 50, sorry.
Yeah. Because I'm getting myself all kerfubbulated. Yep, good point. So now if we calculate all that stuff, we're going to get this one's, let's see. There's a negative in front of this one and a negative there. We're going to get a positive. There's a negative and a positive. This is going to be a negative value. A negative and a positive. This is going to be a negative value. And we sum them all up. So we need to calculate. And guesstimating.
Is that a pretty high value?
Say again?
Is that a pretty high value?
Well, it's 13,600 times almost 10 times 0.9, 9 to the 9 to 8, 8 times 36. But if you put kilo, if we want to know in terms of kilopascals, we have to take another 1,000 out of it. So it's not going to be like, it's going to be a huge number, but pressure-wise it isn't huge.
I got 10,876.
10,876?
I didn't convert, so I actually got 108,768. But you said take 1,000 out, so it would be 10,876.
Well, no. Say again. What did you get? Was your whole thing? What 10?
Before converting.
Yeah.
Okay. 108,768.
108,768.
But if you take 1,000 out, then it'll be 10,876. That's not for the first line. I'm saying the whole thing.
Oh, okay.
So
Well,
the first line I got 119,952.
119,952, and that's no decimal points.
I didn't convert, no, and that's no decimal.
That sounds. Does that make sense to me? Let me think about this a minute.
I basically just did
Yeah.
13,000 times 9.8 times 29.
Yep, and I'm thinking, oh, that sounds like, wow, it's atmospheric pressure, how can that be? But thinking about it, is that reasonable? And you always got to think, you're not always going to have an answer book to tell you what the answers are, and you have to think, is that reasonable? We got 0.9 meters of mercury to start with, and 760 millimeters, which would be 0.76, would be about 1 atmosphere, and we're talking about 1 atmosphere. So yeah, I'm thinking we're good. And so what's our second? What's the second number?
I got 6284.25.
And third number?
I got 4,900.
And altogether you got a 10.
108,768. Yeah. But
And we know for the numbers we're working with don't have more than like 2 digits of precision. That might be only 1, that might be 2. So what we know for sure, maybe it's 109.
We got 108.9 kilopascals in the end.
Yeah, we're ballparky. That's getting into sort of rounding error sort of thing. It's basically going to round to.
On every one of those 3 things. I got 12,0074.4 minus 62,90.665. And I did the exact same thing he did. 13,600 times the next one.
Yeah, do the 9.
I need 9.8.
Yeah, so 9.8 versus 9.8.
81 is what I did. I just did what you did, 9.81.
Yeah, so we're in the ball. All of those are going to round up to about 110 kilopascals. So what we know for sure is air pressure gauge is going to be around 110 kilopascals. This is way too much information at this point. And we got, depending on rounding errors, again, all the numbers I'm hearing are right with using different numbers for, 9.8 versus 9.81 versus a 9.807. They'll get you different results, but based on what's driving it, it's 1, maybe 2 digits of precision, possibly 3, but it's probably more like 2. So if we got 2 digits for precision, it's 110 kilopascals would be the air pressure in there, in spite of the fact we got 3 fluids that we're dealing with in the meanwhile. And we got other things that would enter into it, speaking of, how hard are the numbers. Densities are pretty tight, except they're set for a particular temperature. So mercury will have a different temperature or different density at, boiling temperature than it does at 50 degrees Fahrenheit or, 10 degrees centigrade. The oil will expand and contract even more with temperature. But those terms are relatively small. The one that's really driving it is the mercury temperature. So if you're needed more precision, you want to make sure you measure these with better precision, and then factor this in density relative to temperature. These were round numbers. If you look in your book, it almost never says that water is 1,000 kilograms per cubic meter. But at some temperature, like 2 degrees C, it is. I mean, when it's ice water, it's really, really, really close to that number. And it's basically kilograms are originally defined in terms of 1,000 kilograms with 1 cubic meter of water at ice water with no ice in it.
Question for you.
Yes.
So I'm following most of this, except for I'm a little confused on why for the pressure for the atmosphere we used a 0.
The reason for that was we were doing a gauge pressure. So how much pressure is there in the room? Like, there's no pressure in the room. Well, there is pressure in the room, but relative to the pressure in the room, it's not different. The pressure in the room isn't different from the pressure at the top of the that where the air is meeting the water there. So yeah, that's a little funky on that, but basically because we want to know what the gauge pressure is, what the gauge would be comparing it to the air, and the difference between where the gauge would be on the tank and the top of the fluid column would be 0. Yeah.
What does he give us the air density?
Just because, no good reason, you don't use it. What's actually true, if you could have also had an air, a loop in there that included air.
But it'll be from third density and height as well.
Yeah, maybe you're separating the mercury from the oil with air, which probably is a good idea. If you did that, you'd have rho GH for the air also. But what does it say?
1.2.
Yeah, 1.2 kilograms per cube. So, like that tank in the back of the room, I like to use because that's a what they call a uniform bulk container. It's about a cubic meter. So the air in that weighs 1.2. It's 1.2 kilograms, but it would be 13,000 kilograms, or almost 14,000 kilograms if it was full of mercury. And the density of air is so much, it's real, there would be a number in there, but if your precision isn't getting to that level, you don't have to deal with, it's washes out in the rounding when you have something that's that. There would be a height, you'd have to measure the air thing and then the next, but it's, water's 1,000 times heavier and oil's 800 times heavier. So that height of air, it would be a real pressure, but it would wash out with your precision. Okay. By golly, I think that about does it. We have, that takes care of chapter 1, chapter 2. Tomorrow we'll start on chapter 3.